Welcome to While We Were Distracted, the podcast where we explore topics that often get overshadowed in the rush of daily life.
Today, we're strapping in for a really high-altitude look at aerospace manufacturing. Specifically, we're focusing on the European giant, Airbus. They've just been hit by this set of simultaneous and, frankly, extraordinary challenges. I mean, it feels like they were ripped from two completely different disaster movies. Our mission today is to unpack this dual crisis facing the foundational workhorse of their fleet, the A320 family. We have two completely distinct problems running at the same time. One is this sophisticated high-tech safety crisis triggered by, and this sounds crazy, literally cosmic forces. And the other is a very fundamental, very messy quality flaw in the physical structure of the airplane. And both are happening at just the worst possible time, threatening to derail their really high-stakes annual delivery targets.
You really can't overstate the importance of the A320 family here. It's not just a cash cow for them. It's the most delivered jetliner in the world. It recently overtook the Boeing 737. So when you have an assembly line operating at this kind of massive scale, designed for maximum volume and speed, any systemic flaw, whether it's digital or mechanical, it just tests the absolute limits of safety integrity. This situation really forces you to look at that tightrope walk, that balance between getting planes out the door and, making sure they're perfectly safe.
That sets the stage perfectly. So let's start with the one that feels like science fiction, the solar flare scare. Okay, let's unpack this, beginning with what triggered the largest recall in Airbus's entire 55-year history. Because this wasn't just some proactive maintenance schedule, right? This was a massive emergency response that came after a real-world incident in midair.
That's exactly right. The immediate cause came from an incident back in October. It involved a JetBlue A320 flying from Cancun to Newark. And the plane just suddenly dropped in altitude. It was serious enough that they had to do an emergency reroute. So when the investigators dug into the digital wreckage, they found this stunning vulnerability. They said, and I'm quoting here, that intense solar radiation may corrupt data critical to the functioning of flight controls.
Solar radiation, you mean? High-energy particles from space are interfering with these complex digital systems. I thought these things were designed to be fail-safe. It sounds like a pretty fundamental design problem.
It is, but it's a very specific kind of problem that engineers call an SEU, a single event upset. Think of it this way. The sun, it occasionally spits out these high-energy protons and cosmic rays. These particles are so powerful that if just one of them happens to strike a specific transistor in the avionics computer's memory, it can physically flip a bit. It can change a 0 to a 1 or a 1 to a 0, and that single flip can instantly corrupt critical flight control data.
Wow. And if that data governs how the plane flies, that could be catastrophic.
Precisely. The system that was affected was the elevator aileron computer, the ELIC for short. This is the computer system responsible for regulating the plane's pitch.
So the up and down angle of the nose.
Exactly. So if the ELIC gets corrupted input from a solar ray, it might momentarily think the plane is pointing somewhere it isn't. And that causes a sudden, uncommanded input from the controls, which is what led to that really alarming altitude drop on the JetBlue flight.
And the cosmic timing here is just like, it's kind of unavoidable, isn't it? The sun is entering a much more active cycle, so that means more solar flares, more of these geomagnetic storms.
That's the broader context, absolutely. Solar activity operates on roughly an 11-year cycle, and we are entering a peak period right now. Scientists have been tracking an uptick in activity since about 2008, and the concern for aviation is that the digital components on modern aircraft, they're incredibly sophisticated, but they're also running hotter with smaller, denser microprocessors than ever before, and that makes them potentially more sensitive to these high-energy particle strikes.
So this emergency alert went out for 6,000 jets. That's more than half of the entire global A320 fleet. How on earth do you execute a recall that fast?
Well, it required unprecedented speed and cooperation from airlines all over the world. The good news is that for the vast majority of those 6,000 jets, the fix was relatively simple. It was a software revert. They just rolled back the operating system of the ELIC to an earlier version, a version that crucially did not contain this vulnerability. And maybe it had a slightly different architecture, more simplified code that was just less susceptible to that specific type of solar-induced bit flip.
So the quick fix was basically to go back to the system that wasn't broken.
Exactly. It took about 2 to 3 hours per aircraft, uploaded securely right there in the cockpit. And what's really fascinating here is the speed. The entire industry mobilized instantly. The fixes were implemented far faster than anyone expected. The vast majority, as they put it, were modified and back in service within just a few days. It was, frankly, a masterclass in crisis management execution.
But speed didn't solve everything. There's a really crucial sticking point for a subset of the older aircraft.
Yes. While the main fleet got that software patch, about 900 older aircraft, the original estimate was around 1,000, but still 900 is a huge number. They require a complete physical hardware replacement, and this gets into the weeds of avionics architecture. Their older computers simply can't handle the software patch or the rollback effectively, so they need a new generation of hardware to fix the vulnerability.
And a hardware replacement is a whole different ballgame than just uploading some software.
It creates a supply chain crunch immediately. A new computer system isn't something you can just pull off a shelf in bulk. Industry sources were indicating this complex replacement could take several weeks per plane, and that's primarily due to limited supplies of these specialized new computers. So while the immediate safety crisis was resolved for, 90% of the fleet, a pretty significant chunk of older aircraft is now facing a prolonged grounding or at least operational restrictions.
And right as this enormous, rapid software repair was happening, the Airbus CEO, Guillaume Faury, he issued a public apology. It sounds basic, but that was a major strategic move, wasn't it?
Oh, it was incredibly significant. If you connect this to the bigger picture of aerospace crises over the last few years, Airbus made a very conscious decision to prioritize immediate, transparent action over, say, operational secrecy. They wanted to show they were taking the safety concern, even one driven by cosmic rays, with the utmost gravity.
But isn't that a bit of a double-edged sword? I mean, yes, they look transparent now, but they've just confirmed their planes are vulnerable to cosmic radiation. Doesn't that invite even more intense regulatory scrutiny than if they had just quietly issued a service bulletin and, did the fixes out of the public eye?
That is the core tension of modern risk management. It really is. Airbus is betting that some short-term public scrutiny is preferable to the catastrophic, long-term reputational damage that opacity can create. They effectively just said, yep, we found a safety flaw, apologized for the disruption, and then fixed it instantly. They chose to frame the narrative as, we found a risk and we acted faster than anyone expected. That's a very different narrative than we tried to hide a risk. And that whole shift in strategy is a direct result of lessons learned from their competitors.
So the world's focus is on this cosmic threat, which was resolved pretty quickly for most planes, and how the company handled the crisis. But here's where it gets really interesting. Just as the dust was settling on the biggest recall in their history, a brand new, fundamentally different problem landed right on their doorstep. A quality flaw.
A flaw that's entirely physical and entirely local to the production process. Airbus confirmed they'd encountered an industrial quality issue. It was affecting metal panels that form the outer skin of the fuselage on a limited number of A320 family jets currently on the production line.
50 planes caught in the assembly process, I think some reports said. Why does that number 50 feel so significant compared to the 6,000 planes that needed a software fix?
Because the software fix impacted planes that were already flying. That makes it a safety issue, this quality flaw. It impacts planes that are ready to be delivered, and that makes it an immediate, guaranteed financial bottleneck. The problem originated with an unnamed external supplier, some vendor that manufactures these highly specialized metal panels.
And the production process for the A320 is famously distributed, isn't it? You've got components coming from all over Europe. The front fuselage from France, the rear from Germany.
Exactly. Aerospace manufacturing is this symphony of hyper-specialized global suppliers. So when you have a critical component like a fuselage panel, this thing has to withstand enormous stresses. And it's found to have a structural or manufacturing defect from a specific supplier, the entire system just grinds to a halt. Now, Airbus assures us they've identified the source, they've contained it, and confirmed no flawed panels reached aircraft already in service. But the immediate result is that 50 jets, which should be rolling out the door and generating cash flow, are now stuck in a complex rework process.
Yeah, this isn't like uploading new software. Fixing a faulty structural panel.
Yeah.
That means stopping the assembly line, accessing the area, maybe removing other components, replacing the panel, and then recertifying the whole structure.
It's a complete stoppage of momentum. And it's more than that. Once you identify a flaw with a critical supplier, you don't just fix the 50 planes, you have to then initiate a massive quality audit on that supplier's entire process. You might have to pause their contracts, maybe seek out secondary suppliers. This kind of supply chain repair can take months, which far outpaces the, 2 to 3 hour fixed time of the solar software issue, it really highlights the fragility of modern lean manufacturing in aerospace.
And the market reaction just speaks volumes about the severity. The discovery of this physical quality flaw caused a dramatic stock market. Dropped Airbus shares fell as much as 11% initially. That financial drama actually eclipsed the initial headlines about the cosmic radiation safety grounding.
This is that financial paradox that we really need to dissect. Why did the stock market punish a delay in delivering 50 planes more severely than the risk of solar radiation on 6,000 planes? It all comes down to how you price risk. A safety issue, like the solar vulnerability, it's systemic, but it's also regulatory. Investors trust that the company, under regulatory pressure, will fix it. And in this case, the fix was mostly quick. The future cash flow is still secure.
But the quality flaw.
That's a direct, guaranteed, and immediate hit to their cash flow. Deliveries are how these manufacturers get paid. So when 50 jets are grounded in the final production phase because of a structural flaw, that means guaranteed delays in revenue. The market sees that delay and prices in the risk not just of those 50 planes, but the potential for the supply chain issue to extend even further into their 2024 production guidance. It hits the bottom line, and it hits it now.
So let's look at that financial goal that's under threat. Airbus's massive reliance on A320 production means this double pressure, the residual fallout from the solar recall plus this new quality flaw, it directly affects their year-end goals.
And that year-end goal has always been ambitious. Airbus is targeting around 820 deliveries for the year. But their throughput in November was actually lower than they'd anticipated. They only hit 72 jets, which left the year-to-date total at 657 aircraft.
So what does this all mean for December? To hit that 820 goal, they're facing what analysts are calling an astronomical task. They need to deliver more than 160 jets in the final month of the year.
Which requires perfect execution, 0 delays. Every single logistical component has to be functioning optimally. And industry sources and analysts all agree the fuselage quality issues, they could not have come at a worse time, end quote. Airbus was already dealing with pre-existing logistical issues, things like repair bottlenecks, grounding hundreds of other unrelated jets because of engine or component supply issues. They absolutely needed maximum output right now.
It sounds like they're fighting on two fronts. They're simultaneously fighting a kind of historical ghost, the lingering hardware fixes from the solar recall, and an immediate enemy, this physical flaw that is actively stopping jets from being delivered today. It's the ultimate twin pressure point.
It is the defining moment that reveals just how tight the margins are in aerospace. You have to maintain the highest possible safety standards, which sometimes requires a mandatory, fast slowdown like that solar recall. But at the same time, you have to manage production volume to meet financial guidance for shareholders. The quality issue forces an unscheduled structural slowdown, and that is what panics the financial markets. It's a clash between engineering safety and shareholder expectations for growth.
Absolutely. So to wrap up this deep dive, you've seen two fascinating concurrent challenges facing Airbus. A massive cosmic safety threat that required the biggest recall in history to protect jets already in service, which they managed to handle pretty well through rapid software deployment. And then this distinct ground-level supply chain quality flaw that's actively endangering planes waiting to be delivered, which impacts their immediate profitability.
And these challenges, they really highlight that in the modern aerospace sector, the pressures of speed and volume have, well, they've reached a kind of breaking point. A point where the slightest deviation, a cosmic ray hitting a microprocessor or a tiny flaw in a metal panel from some external vendor, can instantly derail the entire corporate calendar and its stock performance.
And that leaves us with a final provocative thought for you to consider. Given the high stakes, the pressure for these record production numbers, and the global reliance on these incredibly complex supply chains, how will the industry fundamentally shift its structure to balance that drive for volume and speed with the necessary periods of slowdown, transparency, and auditing required to maintain absolute safety and quality standards? Will we see a move away from lean manufacturing to build in necessary buffers, or will this tension just continue to intensify?
Don't forget to like and subscribe for the next episode on While We Were Distracted.